So this term is focused on federated learning with frustratingly easy neural domain adaptation. And yes, there'll be an acronym coming for that, so you don't have to say it every time. I worked with Amrit, David, and John. And so let's start with probably a question that might be on your mind, which is what is federated learning? So if you've heard about it, cool. But federated learning is a technique to train models where the data exists. So for this example in the graphic, imagine that you're the model owner and you have Joe, Jane, and Jack. You don't own their data, but you'd still like to build models that leverage their data. So we can develop like a server client model division where you build an updated model, a server model based on models that are trained on Joe, Jane, and Jack's data. And this is especially useful when you don't have direct access to the data for sensitive situations. So healthcare is a pretty good example of where federated learning can be used. And then the next part of my little title, which is what is frustratingly easy neural domain adaptation, which I'll be now calling as FENDA because it's very long. So this approach was originally designed for domain adaptation, which from the research I've conducted is broadly when you'd like to construct a model to perform a similar task for a new domain. So for example, if it was some sort of like item association task and you're given the word apple in the domain of fruits, an apple is a fruit, but in the domain of say companies, apple is the company that you're likely familiar with. And so in this technique in FENDA, they try to use local and global components. So here in the diagram, the H sub t with superscript k corresponds to a set of parameters for a local, like a local set of parameters, and the H sub t without the superscript corresponds to the global set of parameters that's used to manipulate the input x sub t. And so already we can draw some parallels between this approach and federated learning. Particularly in FENDA, there's a local component for the domain and a global component for a domain. And we can treat domains as data sets to say that we can build local models on a given data set, which could correspond to a certain hospital's data. And then each of those models could have a global component that is updated using the data across multiple hospitals, for example. And so how would we combine these two approaches? And really, how do we measure performance of a model that combines these approaches? So we know that for traditional federated learning tries to create a global server model that performs well on all data sets, while a federated learning with FENDA approach would create client models that have local and global components. So rather than creating one model that attempts to or that performs well on all of the clients, we can build client-specific models. And so the questions that arise after this are, okay, how do we create an architecture that best uses the local and global components? And as a starting point, can we create global layers? And which layers should we make global? These are all questions that I attempted to answer, or at least attempted to create approaches towards throughout my term. So we can try a simple experiment with the baseline federated learning implementation and other federated learning with FENDA approaches. So if we take a basic example of like the CFAR10 data set and a simple model with two convolutional layers, two fully connected layers, and then an output layer, our like experimental design is going to be training training several models on splits of the data for two epochs, sending the shared components of the model. So in this case, it's the entire model back to the server, which then returns models with aggregated weights. Here we're using a simple averaging strategy. And in this baseline, we're going to produce a global model that should perform well across all of the given splits of the data set. So the important thing to remember about the baseline approach is that the metrics we want to track at the end of our training or at the end of our processing are at the global level. So what is the performance of the updated model that's built on the server side, rather than the performance of specific client level models. And that's different from the approach we're using with FENDA, which is a similar process, but duplicates layers it has duplicated layers from the the baseline approach. So we might have a duplicated conv layer or a duplicated fully connected layer. And the simple strategy that I tried to use was concatenating the output tensors from these layers to produce a new tensor that could be then further processed. And in contrast to the baseline approach, this approach creates client models with global information. And that global information here is global layers. So the important metrics to track here are going to be client level rather than server level. And so with a simple experiment, we can conduct our simple experiment and get some results. Here I'm focusing on accuracy to get a high level understanding of the performance of different approaches. And as you can see, the FENDA approaches tend to either perform similarly or better than the baseline federated learning. I also noticed that with more global layers, the models tend to perform better in client accuracy, which might suggest the intuition that the models can improve with information about the other clients. And so the new questions that come out of this specific experiment are particularly in the number of decisions we had to make. So for one, the results I had before, I'll go back. The results here are obtained by manually selecting the layers to be duplicated. So in the second example, FENDA with global layers, that is a model that's constructed with every layer except for the output layer as a duplicated layer, while the third example is just the convolutional layers. But you might imagine that these kinds of things are almost decided before the model is constructed and doesn't take into account any information that might be collected during training. And the next part that comes after that is, can we extend this approach to any models? Are there restrictions on the kinds of models this approach would work for or would not work for, And then for arbitrary models, which layers, what is the strategy we should use when deciding what information should be exchanged between clients? And then the strategy we used here was a simple averaging strategy, as in when the server collects models or model weights from clients, it simply averages them and then sends back the average result across all the clients. There are a wide variety of different strategies to exchange weights that exist in literature. And I guess this experiment was conducted with averaging, but I'm curious to see how other weight exchange strategies would change or improve performance. I want to give a huge thank you to Amrit, David, and John. Without your support, I don't think this would have been possible. Thank you.